Ever get that weird feeling, when you're stuck in traffic and it feels like forever, but then a great vacation just poof, flies by?
Yeah, definitely. Time feels subjective.
Well, believe it or not, that feeling actually connects to some really deep truths about the universe. It sounds like sci-fi, but it's real
It
physics.
really does. Einstein territory.
Exactly. Today, we're plunging into relativity, drawing insights from Exploring Black Holes, Introduction to General Relativity by Taylor and Wheeler.
Oh, that's a great one. Wheeler and Taylor, giants in the field. They make some really complex stuff, surprisingly, well, graspable.
Right. Our goal today is to explore how gravity and speed, fundamentally warp how we measure space and time without getting lost in the heavy math, hopefully.
Just looking for those aha or maybe whoa moments.
Totally. Okay, let's dive right in. So, one of the first big ideas is that space and time aren't these separate things we kind of experience day to day.
Yeah, the book hits you with it straight away. Space-time is a unity. It's fundamental.
A unity. So, not just space and time, but space time.
Exactly. Think of it like a fabric. A four-dimensional fabric that weaves together the three dimensions of space and the one dimension of time. Everything happens within this space-time.
So, an event isn't just where it happened, but also when it happened, and those are locked together.
Precisely. It's a coordinate in space-time. Location and time, inseparable.
Okay. Okay, so if they're linked like that, messing with one or like moving really fast must affect the other, right? Time.
That's where it gets really interesting. Relativity tells us time isn't universal. It's relative.
Which brings us to wristwatch time. What's the deal with that?
Right. Wristwatch time, or proper time, it's simply the time measured by a clock that's moving with you, the observer. Your personal time.
My personal time.
Yes. And here's the kicker. How fast that clock ticks, how you experience time, depends on how you're moving relative to other things.
Whoa. So my watch and your watch could genuinely tick at different rates if we're moving differently.
Absolutely. It's not just an illusion or a measurement error. Time itself flows differently. The book uses an example like a stone flashing light in space.
Right, I remember that. If I see flashes every second, someone zooming past might see them happen slower or faster on their watch.
Exactly. Their motion relative to the stone changes the time interval they measure between flashes.
Hmm.
It's actual time dilation.
Mind blown. And there's math for this, you said.
Oh yeah, there's a formula to calculate the precise difference in wristwatch time. We don't need to get into it, but it's solid physics.
Good to know it's not just hand waving. Okay, another concept. The principle of extremal aging sounds very grand.
It does, doesn't it? But the idea is, well, kind of elegant in a weird way. It says that a free particle, one with no forces acting on it, traveling between two events in space-time,
Yeah.
it will naturally follow the path, its world line, that maximizes its total proper time, its wristwatch time.
Hang on. Maximize. So it takes the path where its own clock ticks the longest, not the shortest distance.
Correct. It seems counterintuitive from a purely spatial perspective, doesn't it? We think shortest distance.
Totally backwards.
But in space-time, the straightest path, the path of inertia, is the one where the most time elapses for the object itself. It's like the universe prefers things to age as much as possible when left alone.
Okay, my brain is officially doing contortions now.
Yeah.
All right, next up. Free float frames. The book says these are local. What's a free flow frame?
Think of a small, isolated region of space-time where gravity seems to disappear locally.
Ah, like the falling elevator thought experiment.
Exactly. Inside that falling elevator, you and everything else are accelerating downwards together. So relative to the elevator, you feel weightless, gravity seems gone. That's a local free flow frame.
Okay, so locally gravity vanishes. Why is the local part so important?
Because gravity isn't perfectly uniform. Even in that falling elevator, if it were huge, say Earth-sized, you'd notice tiny differences.
Different.
Yeah, tidal forces. The part of the elevator closer to Earth is pulled slightly stronger than the part further away. Over a small distance, you don't notice. But over large distances, these variations, these tidal accelerations, reveal that gravity is still there, just not uniform.
Right, like the moon causing tides on Earth, different poles on different parts. So for experiments on relativity, you need a space small enough that these tidal effects are negligible.
Precisely. You want to isolate the effects of space-time structure itself, not these variations in the gravitational field. You need a truly inertial frame locally.
Got it. Okay, so how do we actually measure things in this potentially warped space-time? The book mentions an observer with a lattice of clocks. Sounds complicated.
It's a conceptual framework, really.
Yeah.
Imagine this observer sets up a vast grid, a lattice, extending through space, and at every intersection point, there's a clock.
A clock everywhere. Wow. But how do you get them all perfectly synchronized? Especially if time runs differently depending on where they are, potentially.
Ah, good question. Synchronization is key. They use light signals. The observer, maybe at the origin of the lattice, sends out a light pulse.
Okay.
When that pulse reaches each clock in the lattice, that clock is set to a time that accounts for how long it took the light to travel from the origin to that specific clock, since the speed of light is constant in a vacuum.
Ah, you can calculate the travel time precisely, so you end up with this network of perfectly synchronized clocks.
Exactly. And recording rods for distance. This whole setup allows the observer to pinpoint the exact location and time of any event that happens within their reference frame.
It's like a perfect space-time coordinate system. Clever. Okay, now for the big one. Gravity. We think of it as a force, Newton's apple. But Einstein, he said it's curvature.
He did. General relativity completely reframes gravity. It's not a force pulling things across space-time. Instead, it's mass and energy warping the fabric of space-time itself.
Warping the fabric. The bowling ball and the rubber sheet analogy comes to mind again.
That's the classic visualization, and it's helpful. The bowling ball, mass, creates a dip in the sheet, space-time. A marble rolling nearby curves towards the ball, not because of a direct pull, but because it's following the curve of the sheet.
So planets orbit the sun because the sun's mass creates a huge dip in space-time, and the planets are just following the curves.
Essentially, yes. They're following the straightest possible path, called the geodesic, through that curved space-time. Even light follows these curves.
Wow. And the book mentions the Schwarzschild metric that describes this curvature mathematically.
It does, specifically for the space-time around a non-rotating spherical mass like a star or a black hole. It's the geometry equation for that situation.
Geometry is gravity. Okay, then the book does something else weird. Measuring mass in units of length. Kilograms to meters. How? Why?
Yeah, that sounds odd at first. But in general relativity, where geometry is king, it's actually very convenient. Mass is a source of space-time curvature, which is geometry. So expressing mass in geometric units like length makes the equations cleaner and highlights the connection.
How do you convert them, though?
You use fundamental constants.
Yeah.
The gravitational constant g and the speed of light squared, c/L. The conversion factor, m meters, g/c/O links mass directly to a length scale associated with its gravitational influence.
And the book gives that factor, right? Something tiny.
Yeah, about 7.424, a 10 centimeters per kilogram.
Okay.
For everyday objects, this mass length is minuscule.
But for something like a black hole,
Then it becomes significant. It relates directly to the size of the event horizon, for instance. It tells you the scale at which that mass dramatically warps geometry.
okay, connecting mass directly to geometry. Makes
Yeah.
sense. Sort of. Now, what about gravitational redshift? That sounds like the Doppler effect, but with gravity.
It's related to another consequence of curved spacetime, gravitational time dilation. We said time runs differently depending on motion, but it also runs differently depending on gravity.
Runs slower in stronger gravity.
Exactly. Clocks deeper in a gravitational well tick slower relative to clocks farther out. So imagine light climbing out of that gravitational well, say from the surface of a star. It originates where time is running slower. By the time it reaches us, where time is running faster, weaker gravity, its waves appear stretched out, shifted to lower frequencies.
Lower frequency means redder light. Gravitational redshift. It's not moving away, it's just climbing out of a time warp.
That's a great way to put it. The difference in the flow of time causes the redshift. It's a direct consequence of space-time curvature affecting time itself.
Incredible. Okay, the book also mentions orbits and something called an effective potential. What's that about? Is it like the shape of the space-time dip?
It's a useful mathematical tool, yeah. It helps visualize the possibilities for an object orbiting in curved spacetime. It combines the effect of the gravitational dip with the object's own energy, and crucially, its angular momentum, how much it's swinging sideways, essentially.
So depending on its energy and spin, it might settle into a nice circular orbit.
Or a precessing ellipse, where the orbit itself rotates.
Yeah.
Or if it doesn't have enough angular momentum or has too much energy, it might just plunge right in. The effective potential shows you these different regimes.
So it maps out the dynamic possibilities in that curved landscape.
Cool. And I bet near a black hole, that landscape gets really extreme.
Oh, absolutely. The book touches on what you might see near or even falling into a black hole, extreme distortions, light bending, completely alien vistas.
Okay, wow. This is all fascinating, mind-bending stuff. But does any of it actually matter in our everyday lives? It feels so astronomical.
You'd be surprised, the book brings up a fantastic example. The Global Positioning System, GPS.
GPS, my phone navigation, how?
Well, GPS relies on a network of satellites orbiting Earth, right? And they have incredibly precise atomic clocks on board.
Right, for timing signals to figure out location.
Exactly. But those satellites are moving very fast, and they're in a weaker gravitational field than we are down here on the surface. So both kinds of time dilation are happening. Special relativity from speed and general relativity from gravity.
Precisely. The clocks on the satellites actually tick slightly faster than identical clocks on Earth. It's a combination of them ticking slower due to their speed, but significantly faster due to being in weaker gravity. The gravity effect wins out.
Faster. By how much?
It's tiny microseconds per day, but GPS needs nanosecond accuracy. If engineers didn't constantly account for these relativistic effects, both special and
The
general,
whole system would fall apart.
the positioning errors would build up incredibly fast. We're talking meters of error within minutes, kilometers within a day. Your GPS would be useless. It only works because we account for Einstein's theories of relativity.
That is absolutely stunning. So general relativity isn't just about black holes. It's actively working inside my phone right now.
Every time you use GPS, you're relying on it.
Okay, let's try and recap. We've got space and time unified into space-time. It's not absolute, it's relative. Gravity isn't a force. It's the curvature of space-time caused by mass and energy.
And this curvature affects everything, how objects move, how light travels, even how time itself flows.
Leading to things like time dilation, gravitational redshift, and needing corrections for GPS. It paints a picture of a universe that's way more interconnected and, well, weirder than it first appears.
Definitely more dynamic and fluid than our everyday intuition suggests.
So maybe the next time you check your watch, or especially when you use GPS, just remember you're tapping into these profound mind-bending effects of Einstein's universe. It makes you wonder, doesn't it? What other things we think are fixed and solid might actually be relative, something to chew on.
Absolutely. And if this has piqued your interest, Taylor and Wheeler's Exploring Black Holes is a fantastic place to continue the journey. It really opens up your perspective on reality.